Hello, everyone. We're going to spend the next 30 minutes discussing VSM and how we're planning on emulating it in QEMU and KVM. My name is Nicolas Saenz. I'm a hypervisor and KVM engineer at AWS. We build a Nitro hypervisor, which is the hypervisor that powers EC2. So it's a mix of KVM and a proprietary user space. And yeah, every time you launch an instance through EC2, it goes through Nitro. The talk is going to be a mix of me re-explaining what VSM is and why we want VSM. And then I'm going to discuss how we managed to get all these integrated within QEMU and KVM. The ideas that were great, and probably the next steps, and how all this is going to eventually pan out into a common framework for VMPLs, TDX, and VSM. So VSM is a bit different than other confidential computer features. There's a different security promise here. So although some concepts are similar, the end result is very different. The idea is called virtualization-based security. And what we want to do is protect the guest against itself. So if at some point your guest gets compromised, we might be able to leverage the hypervisor to harden it. So this is your typical hypervisor stack. We generally sit in that red boundary. VMs have absolutely no visibility in what the host is doing. They cannot really introspect. But on the other hand, the hypervisor has full visualization on what's happening in the VM. That creates, on non-confidential computing workloads, a necessity for VMs to trust their hypervisor. In more formal parlance, I think that means the hypervisor belongs to the trusted computing base. That's something we can leverage to harden the guest. Just to give you a high-level example, once a VM is running, it might have a set of secrets, and by secrets I mean pretty much anything, binaries, data, photos, whatever, CPU state as well, and some policy that decides who gets to access those secrets. Again, very broad, read-write memory access to a file, or yeah, whatever framework the operating system uses to control access to secrets. And within that context, it's very possible for an attacker that has gotten control over the operating system to disable the policy and, yeah, access those secrets. That's what virtualization security might be able to protect and avoid by moving both the secrets and the policy down into the hypervisor. Okay, it is very abstract, so I'll give you a little example, so at least you get an idea where I'm coming from. Again, a secret in memory, some read-only memory that the VM wants to remain as such. An attacker gets kernel access and manages to update the page tables, so now it's able to modify the memory. And that's it, you're compromised. But one thing the VM could do, if the hypervisor was enlightened to do so, and the VM as well, it could request the hypervisor to ensure that that memory is read-only. And not only that, it could also attach some policy to that promise. So whenever this attack happens again, the hypervisor can stop it, and through that policy that was attached to the read-only request, inform the VM of what happened and allow the VM to introspect itself and realize what was happening. Of course, in the whole process, the memory will remain read-only, which is very nice. It's not only about memory. The hypervisor has full control over the system, so we couldn't introspect pretty much on every aspect of the virtual machine lifetime. Okay, in comes VSM. So VSM is a way of, it's a framework that allows virtual machines to do this. it was introduced by Microsoft. It's a spec, so it's commonly known as the TLFS, and there's nothing really Microsoft specific within that spec, so there's nothing preventing us from implementing this one-to-one in QEMU and KVM, and also there's nothing preventing Linux guests from using all this framework, so it's fairly flexible. For now, it's only x86 specific, but there's work going towards ARM64 as well, but we won't know much about it until they publish the spec. But as far as I've heard, the hypercall spec is going to be very similar, so all I'm going to explain now, it's going to map to ARM64 as well. One of the core concepts VSM introduces is a concept of virtual trust levels. And again, this is going to be very similar to VMPLs, which we've been discussing in the past. A virtual trust level is an execution context the CPU might be in. And CPUs now have multiple of those execution contexts. Those VTLs are hierarchical, so we consider VTL1 to be more privileged than VTL0, and so on and so forth. There's only 2 here, but we can go all the way to 16. The hypervisor is the one that does the work of switching from one VTL to the other, and when it does so, it saves the state of the dormant VTL, and it's the one that knows how to do those state transitions. There's 2 hypercalls to do that, VTL call and VTL return, and the semantics of how all that works, it's explained in the TLFS. The most important thing here is that each VTL has some private state that, again, the hypervisor has to save, and it also has shared state that it has to mirror on VTL transitions. VTL return, again, as long as VTL1 is running, VTL0 is not allowed to preempt VTL1 because it's higher priority context, and it's going to run as long as VTL1 doesn't explicitly do a VTL return, which goes back into the least privilege trust level. Every VTL also has hierarchy controllers, so they can IPI each other. There's timers as well, so VTL1 can set up a timer, go back to VTL0, and eventually when that timer fires, the hypervisor is tasked to do all the switch. These adds some complexity in the implementation because interrupt routing has to be VTL aware, and we'll see in the next slides how we solve that. VTL also introduces hypercalls to control who gets to see which parts of the memory. So VTL1 can decide to hide some memory from VTL0, or VTL0 can request VTL1 to map memory regions with specific permissions, again, to hide secrets or to protect secrets. The VTL1 also can lock the CPU state in unprivileged VTLs. Again, some registers in the CPU, once the operating system is running, won't really change. So it's very interesting in terms of security. And of course, VTL1 has full visibility over the CPU state of lower privileged VTLs. Each one of these functionalities is a set of hypercalls. I'm not going to go through them because the list is long, but we've managed to implement all of them or parts of them that we cared about with what I'm going to present next. One last thing VSM introduces that's very important, and that goes back to what I was talking about policy. Whenever one of those promises is broken, be it VTL0 trying to access VTL1 memory, or some register changing when it shouldn't, VSM introduces the concept of secure intercepts, and it's a way the hypervisor has to inform a privileged VTL that something wrong happened in unprivileged contexts. And yeah, and that's how VTL1 is going to be able to react to all these events. You might be thinking, what about I/O? DMA could just go and access all that memory. Again, it's up to the hypervisor to fix that. All DMA happens in VTL 0. That's what the spec says. And it's up to the hypervisor implementation to make sure the IOMMU page tables match VTL 0's permissions. I'm not going to go into this topic more because it's more an IOMMUFD problem, but we're working also towards that direction on how to implement that efficiently in QEMU and KVM. Well, in QEMU. So now your virtualization stack looks like this. Within your VM, you're running your normal, what we call the normal world, which is just your operating system. And you have a sidecar operating system. Generally, it can be anything, really, but you'll want a very small operating system that's capable of doing all these operations that I described, locking memory, locking register state, maybe introspecting into the normal world and making sure some structures that are critical haven't changed or have changed in specific ways. There's a lot that can happen there. It's also a nice place to hide keys, for example. And that's something that Microsoft does. It's called Credential Guard. So I want to go back to the previous example I gave, where we want to hide some read-only memory. And normal world gets compromised. The attacker gets to update the VM's page tables. But in this case, well, the access is not going to come through because the hypervisor intercepts it. The hypervisor then issues a VTL switch, injects a secure intercept, a memory security intercept, stating that some CPU did a bad move, and that's it. The secure world gets to introspect into what's been happening, and in any case avoids any of that attack. So where can I use this? Right now, this is only available, as far as the guest is concerned, in Windows. It's pretty transparent. You can use it. You just click some configuration option, Credential Guard, and it will be enabled. In terms of hypervisor, you can use Hyper-V, but you can also use EC2, which supports all these features. And that's for production quality usage. There's some research being done to get Linux to do all this in the guest. And of course, what I'm presenting here is how we've implemented all this in QEMU and KVM. So how do you emulate this in QEMU and KVM? This is the responsibility split when we presented our intention of upstreaming all this last year in KVM Forum. Everything was very KVM-centric. We added VTL awareness to pretty much every single KVM structure, so vCPUs, VM, memory management, APIC, and it didn't work well. It adds a lot of complexity across the board. Especially the APIC part was very, very hard because now you have to enlighten KVM to be able to route interrupts across VTLs and understand who has which priority and so on. And it was very implementation specific for an extremely generic code base. So we had some discussions, and of course we all agreed that it should move upwards into the hypervisor. And I'll now explain a little bit of how we managed to get that done. So this is your VSM VM. The first thing, well, before I continue with this, I want to say something. Since LPC and KVM Forum, we've been sitting down with KVM maintainers, AMD, and other people that are interested in doing this execution context concept in QEMU and KVM. And we've come up with new ideas that we haven't yet implemented that are going to vary a little from what I'm presenting here. It's okay, because the outcome of our conversations matches the overall design I'm presenting here. But keep in mind that the end result is going to be slightly different. So yeah, if QEMU wants to launch VSM VM, what it first does, and I'm simplifying things, it creates two distinct KVM VMs. It now has to track 2 KVM states, which is a challenge on itself because KVM state is kept as a global variable across the board in QEMU. But it does so because it adds a very nice implicit namespacing for APIC and memory management. And we'll see how we use that implicit namespacing to really model VTLs properly. It also creates a vCPU for each KVM VM. So for the case where we have 2 VTLs, we'll double the number of vCPUs. Again, it's a very good container to keep track of all the state of all the vCPUs, of all the VTLs. It works very well in that sense, although it's a bit, it adds a lot of overhead. It also allows us to track, to target specific VTL vCPUs in a very convenient way without having to introduce VTL awareness in the kernel. We were forced to introduce the concept in QEMU of CPU namespaces because QEMU uses the APIC ID to query CPUs when it's looking for a specific CPU. That doesn't work anymore because both VTLs share the same APIC ID. So what we did is create a concept of namespace, and a CPU has both, it's a pair, like APIC ID and namespace, which you can pretty much choose whatever you want. That allows us to query specific vCPUs across QEMU. And that's important because we also had to introduce a VTL scheduler. And it's a little state machine that takes care of doing all the scheduling of the 2 VTL vCPUs as well as passing the state across them. You can see how I've named differently the VTL0 CPU in QEMU versus the VTL1 CPU in QEMU. And that's because an area we want to eventually research is whether we really need a full-blown x86 CPU model for VTL1. There's only so much VTL1 is allowed to do, so I think it's very likely that for the production quality version of this, we'll have to create a specific CPU model for VTLs. We'll see. I can't hear you, sorry.
I just wanted to ask if with the design that we worked on yesterday, will the VTL scheduler still exist?
It can exist. Nothing prevents you from doing one. As long as you don't accelerate through the new design, you still need to do some scheduling. Depends on the fine detail of how we do. Because you're allowed to do the switch outside of KVM with the new design.
In that case, you have 2N threads, right?
2N?
Threads.
Yes.
Okay, so instead with what we talked about yesterday, you have N threads. So you have the VTL scheduler code, but not a full-blown thread scheduler, right?
Yes, yes. And again, these might change once we get the final design, but the ideas are going to be somewhat in the same area. Again, well, it's a discussion in progress, so I can only do so much in that sense. Now, how we solve the problem of having different memory mappings for each VTL. This is, I think, something Sean proposed. And we're using memory attributes. Since we have namespaced KVM VMs, we can target specific VTLs. And memory attributes, which are not upstream, but we sent a patch series already, and we're working on a second one, allow you to switch the permission bits on specific guest page addresses. So now we get per VTL protection, but we also have memory fault exits. So this is just a mechanism that KVM has to inform user space that one of those memory attributes was breached. And it allows user space to then do all the VTL dance to inject a memory intercept. And the last thing we've had to introduce that's like a new change to KVM, it's event polling. So as I mentioned earlier, VTL1's interrupts have precedence over VTL0's execution. So while VTL0 is executing, we need to make sure that VTL1 hasn't pending interrupts. And whenever we get an interrupt, well, we set up a system where KVM sleeps for you within KVM and monitors for interrupts through your regular APIs. And and you get an exit whenever you have a pending interrupt. It allows, again, the VTL1 thread to do the switch and scheduling VTL1. So this is a quick slide just to show how the different KVM VMs isolate fairly well the memory configuration of each VTL, and that's one of the most important things for our design, and the one that was more complex to solve. And I'm going to show you a very abstracted way, a very abstracted picture of how a VTL switch happens now with this new setup. This is the steady state of any virtual machine where VTL0 is running because it's the normal operating system, and VTL1 is just polling for events because it has nothing to do. And eventually, VTL1 had set up a timer, so event polling comes back into user space and notifies the VTL1 thread that, hey, I have a timer. There's some little back and forth with the VTL scheduler that takes care of kicking the VTL0 CPU out, synchronizing the state of VTL0, passing the shared part of the state to VTL1. This is something we don't like at all because it's very expensive to do. And then schedules VTL1. And, well, it might want to poll VTL0, might not. It's not very important. There's a special feature to avoid latency in VTL0 that we can implement. And that's why we want event polling in VTL0. Otherwise, we just sleep until VTL1 returns. This is the final responsibility split. Again, we're happy that VTL awareness is completely out of KVM. And we've been able to introduce low-level primitives within KVM that are most likely useful to other use cases. I haven't talked about all of them, but I think the most important one are event polling and memory attributes. We have some, of course, all these are work in progress, so please don't assume this is ready for usage upstream. But I'll be interested if anyone needs any of these features. I'll be interested in hearing about it and maybe converging on a design that works for everyone. Upstream status, well, those at the top are available as upstream series or are about to be available because we're going to send them this week. Upcoming RFCs, we're working on CPU register filtering, just a broad idea of how we would like to do it, and we'll send it as an RFC and we can start a discussion. And maybe in the future we want to do MBEC-aware memory attributes. As for the upcoming QEMU RFC, I had some ideas there, but I just deleted them because after our discussion with AMD, Paolo, and other interested people, we're going to have to figure out the design. So it's a question mark. Where can I run QEMU and KVM? A VSM with QEMU and KVM? Well, right now you just have to go to our repos, and it's a very proof of concept-y build. So don't expect anything production quality. So I would just use it to research as a research project. But in the future, it'll slowly become a more serious production thing. VSM on Linux guests. This is coming up next year, where we're collaborating with people from Microsoft and want to build a full open source VSM stack. So the idea is to be able to run a Linux guest plus our code in QEMU and KVM and implement all these security features in an open way. Microsoft also announced that they are now using VTL2 and that they moved all their VMM into all their VMM process and device emulation into VTL2. And this is exciting in a way because it's a new paradigm in terms of how we design hypervisors. But it's also a problem with all the design I've been showing you so far, because this requires way more performance than what we can give at the moment. Our current design is very slow, but it's fine for virtualization-based security, because once everything is set up, you don't ever go into VTL1, which is what we want. But once this becomes a reality, and if you want to use this in the Linux world, maybe we have to rethink how to accelerate VSM. And that's where the new design that it's a question mark comes. That's it. Thanks. I'm open to any questions or comments.
Thanks, Nicolas. Are we going to need to have IOMMU FD memory attributes similar to what we have in KVM, or will IOMMU use the same ones as KVM, or yeah, what's going to happen there?
There's not a clear plan on the API itself, but what Jason is working on is implementing the core page table modification operations to be able to do this in an efficient way. That is, cutting a huge page into smaller pages, modifying attributes on specific pages, all atomically while DMA is happening in parallel. So Jason is working on a framework for that. Once we have that, we're going to think about how we connect the two.
Yeah, I wouldn't expect it to be as complex as KVM, because you only have to deal with VTL0, so you don't need multiple mappings. And I'm guessing you probably can't execute. So you just really need to say, be able to say read only, because writable you can do by just punching a hole. So I expect it would be quite simple compared to KVM's mess.
There's also no access.
Right, but you can always just, I assume you can unmap.
Yeah, you can.
Like,
but the problem is how you map in a way that doesn't break DMA.
Yeah. Very random. Can we kill off read-only memory in QEMU and KVM for VSM guests to avoid the further complication where you hit a read-only mem slot that is writable but not readable in the attributes? Just something goofy like that.
You want to disable the option of read-only memory slots just to avoid the...
Yep. That's probably a follow-up question.
There's no write-only memory attributes, I think. No, you cannot do it, I think.
I think what? Okay, so it's because it would cause an APT misconfig. So I think it fails.
Like the PTs won't allow you to express that.
I think that the hypercall would fail.
Sorry, ignore the right thing. A GPA that has a read-only mem slot but is not readable per the memory attributes, because then KVM's existing ABI is that you emulate and trigger emulated MMIO, but it's not readable. So are you supposed to inject default? Are you supposed to exit to user space? Like, can we just avoid that whole thing and say you don't get option ROMs?
XW permissions are illegal. You have exec only, but not exec write.
Right, but I'm saying where the memory attributes for the VTL says you get nothing, complete access disabled, but the mem slot is read only. Then you have to define semantics for which one wins. But can we just kill that off and not deal with it?
So I'm saying it's not hard to define the semantics. We need to see how hard it is to implement them, because the obvious semantics is that the memory attributes win and you cannot access them at all. It always causes an intercept. Then if it turns out to be a pain in the back to implement, then we decide whether to kill it off.
Well, no more questions? Oh, we're done. Okay, sorry. Thank you very much.